I see the flying car industry as game changing when it comes to not only future warfare, but future military operations, just as important, humanitarian relief operations, hurricane support, all the things that we do defense of the homeland. If you start thinking about these devices as nodes in a network, it fundamentally changes the game.
Agility Prime is a program with a vision of world impact. By partnering today with stakeholders across industries and agencies, we can set up the United States for this aerospace phenomenon. Potential outcomes are rewarding and transformative with both military and commercial applications.
I want to offer my congratulations to Dr. Roper and his team for achieving this revolutionary rapid contracting and prototyping method to bring industry and DoD together to develop this new exciting technology with both military and civilian applications. This technology will have great benefit to the needs that we have in Alaska and the Arctic, where conventional aircraft, vehicles, and vessels oftentimes can't operate.
Agility Prime is part of our Defense Department's long history of turning futuristic ideas into reality. I'm proud that the federal government is investing in revolutionary ideas. Agility Prime is leading the way.
This launch of Agility Prime is so exciting. This technology has the potential to make vertical flight more affordable and more widely available. And with the encouragement of the U.S. Air Force and the entire federal government, American companies employing American workers can gain a head start and win a fair share of this lucrative market. eVTOLs have the same agile, vertical takeoff and landing capability as helicopters, but are quieter and should cost much less to operate because of their electric motors.
We are becoming a trusted innovation partner in commercial tech. I could not be prouder of this initiative. I could not be prouder of this team. And I am excited to see how quickly we can go to help commercialize this market for our nation so that our warfighters have options they don't have today, and our nation has an economic advantage far into the future. Innovation is a battlefield, and Agility Prime is just one way we're going to win it.
Agility Prime seeks to ensure a global advantage in advanced logistics technology. Agility Prime can reduce the risk of adversarial commercial dominance, resulting in military disadvantage. As the United States Air Force looks at generating combat power away from runways, those distributed logistics aircraft must be runway independent. This new transformative capability is a promising opportunity to conduct that mission in an affordable and a scalable manner.
Today, we gather for Agility Prime to drive transportation innovation, lower barriers to entry, and expand our partnerships.
We see a time when automation technologies make the requirements on the pilot much less. And we see flying as being accessible to a much wider range of people.
It is truly a great credit to Agility Prime. They could put on this virtual event with so many hometowns of the United States represented. You know, industrial base is not really about just what a country can make. More than that, it's about the people who dream up what to make. And then, of course, those people who make it.
Good afternoon. All right, it looks like we have most of the folks on now. We've got a very exciting lineup today talking about autonomy. Clearly, that is a loaded word. I'll leave it to the experts to describe their various views of that. But before we get into that, a couple of quick announcements that we want to make for the Agility Prime program and for AFWERX overall. As we've discussed over the last month or so, Agility Prime has transitioned under AFWERX, and now AFWERX under the Air Force Research Laboratory. We will, as we've discussed a few weeks back, be kicking off an effort here on the 15th and the 16th. This is a STTR. This is a small business technology transfer program, and it will have a focus area specifically on technologies associated to Agility Prime. So it'll be an open topic, but it will have areas of a focus area specifically on Agility Prime. We'll be giving more details on that in the coming 2 weeks. And then there'll be an opportunity for on the 15th and the 16th to join on a series of virtual events. For those of you who had the chance to participate in the virtual trade show that we held back in April, we're looking to do something similar to that, bringing in more of the research and university partners and talk about how that partnership with research and universities will not only allow a fantastic chance to bring additional research and development into this sector, but also give an opportunity to heighten awareness on the need for the workforce in this particular area. So we're excited to be able to announce that that will be coming out in the not so distant future in partnership with all of the folks across AFRL that are making this happen. The other piece, expecting next week for a broader discussion of this with Dr. Roper joining us here at the beginning of the discussion next week and talking to what that relationship looks like, showing how we are partnering with investors and industry, building that innovation across our ecosystem internal to the Air Force, and then working in all the ways that we can to ensure that development can actually help fuel some of the commercial sector as well. So discussing what that looks like under this new construct. Obviously, this is a construct that has been in development, and looking at ways that we can formalize this, provide additional energy to those efforts as we continue utilizing both the small business approaches, but now starting to look at other ways where we can do the partnering with investors, with industry, with interagency, looking at international partners as well, and how we're doing that internal to Agility Prime, more broadly in AFWERX, and then AFRL partnering across the Air Force. So with that, I'm going to hand it over to a fantastic leader in the Air Force Research Laboratory who is going to talk about the different parts of autonomy today as it relates to Agility Prime, the promise that we have with autonomy into this future, the importance for DoD as we look to ways of reducing our cost and the challenges of training, and being able to create a lot of additional agility to our operators through this potential of autonomy. So I'll hand it over to Frank Delsing. He is the tech lead for Agility Prime, and he will be introducing a fantastic panel that we have today to discuss autonomy. Frank, thanks for joining and bringing together this awesome panel of folks.
Thanks, Nate. I appreciate the chance to talk about this. As Nate mentioned, I'm the technical lead, so I'm looking at things like airworthiness and flight tests and things like that to help the program along as we try to usher in this new age of advanced aerial mobility. So, you know, one of the key enabling technologies that pretty much everybody acknowledges in not just the urban air mobility or advanced air mobility or org or however you want to categorize this space, but across aviation and really across the DoD is autonomy. And before anybody asks the question, because the first question that's always asked when you start discussing autonomy is, what is it? I'm going to leave that to the panelists to help them define what autonomy is. And really, we could probably spend the next hour and a half just on that question alone, but I'm hoping to get past that. And what we're going to do is we're going to have kind of a discussion about more specifically how we see autonomy applying to the space of advanced air mobility, and not just military utility, but civilian utility in that respect as well. So I'm going to start sharing my screen here so that we can jump right in. There's some more of that great artwork from the launch. I couldn't pass it up. I had to include that in there. But just to show everybody what, here's our panel that we have today. And we've got some of the world leading experts on here today. So I'm really excited to hear the discussion. So to start us off, we've got Mr. J.C. Ledet, who is the autonomy technical advisor for the lab. We're going to follow that up with Mr. Wes Ryan, who is an FAA SME, a very experienced expert in what we're going to see in terms of unmanned and pilotless aircraft to come there on the FAA side. Mr. Matthew Catt, who is the chief engineer for our SkyBoard program here in the lab, which is one of our Vanguard programs that is looking specifically at autonomy. Dr. Stephen Cook, who is he's the fellow for airworthiness there at the Independent Office of Airworthiness at Northrop Grumman, but he is also on the ASTM 377 board that is looking at helping to develop and define standards for autonomy, and he can give you some of the specifics there. And then finally, Dr. Matt Dilsaver, who is an autonomy SME here in the lab, also working on a multitude of programs that are looking to take the potential that is autonomy and turn it into an actual capability. So we've got a lot of good stuff to talk about. I don't want to take up too much time because you don't want to hear me, you want to hear them. So just to move straight into it, we'll have Mr. J.C. Lede start us off. He is the autonomy technical advisor. So what does that mean? He is the guy for the lab when it comes to everything and anything having to do with autonomy that the Air Force Research Lab is looking at. He reports directly to the commander on all these things that relate to autonomy, and Agility Prime is one of those things. And so he can give you some details and some background and hopefully some kind of broader scope on autonomy in the lab. So with that, I'm going to hand it off to JC, and I will switch it over to your briefing here on my screen.
Thank you, Frank. I appreciate the introduction, and good day to everyone. It's a pleasure to join this webinar today, and I'll give you some of my perspective on autonomy, and I'll tell you when I do a program review what kind of questions I might ask you if we ever get together. So if you can go to the next slide, please, Frank. So there were already several mention of a definition of autonomy. It turns out that there is an official definition that is adopted for the joint forces, so including the Air Force. It's shown here. I will say in general, I think it's a good definition. It's a little bit long, and I tend to not memorize that much. I prefer my own definition, which I think synthesizes the idea. And basically, autonomy is a C2 construct in which a figure of authority delegates part of that authority to a subordinate. In our case, it's a machine. But the idea of autonomy is really that you let someone or something else do your bidding, but it's always about your bidding. And one of the things I like to really emphasize is autonomy is not independence. I would be willing to bet that in a couple of weeks from now, nobody has been invited to an Autonomy Day barbecue on the 4th of July, right? There is a real difference between autonomy and independence. And that difference is that an autonomous system is put in place to achieve a commander's intent. And that intent includes several things: a explicit objective, take me home, if you're talking to an autonomous car, but also a number of implicit objectives, take me home safely. Although I don't want to have to explain what safely means, it's certainly part of my commander's intent. And finally, there's also an element of preferences, because we all, at the end, somewhat type A's, and we like to do things our way. And so the autonomy or the commander's intent includes those three elements of an explicit objective, constraints, or implicit objective, and preferences. So with this, it leads me to that bottom line here that defines autonomy as a freedom to select a course of action required to achieve a higher authority objective. So next, let's dig a little bit more into what that actually means. If you could go to the next slide, please. Thank you. And from that, you can build a framework of what you're going to need to do when you're going to work on autonomy. And in order to achieve an autonomous system, you'll start with some algorithms. And these algorithms are essentially what everybody would think of when you start working on autonomy. So there's some situational awareness algorithms, so perception, sensor fusion, situation understanding, decomposing that situation into a potential number of tasks, coming up with a course of action, and so on. So those are kind of your basic algorithms. The center pillar for autonomy is a human system interface, because again, if you're going to work on an autonomous system, there will always be a human in the middle of that system. It is the human intent that the autonomous system is supposed to do. So how do you give that intent to the system is really what the human system interface is. It is more than that. It is also continuous monitoring, because one of my friends, who was an expert in autonomy and spent his whole life, said autonomy never works all the time. There are always some special cases where we'd like to at least be able to check what it's going to do before we let it do it. So the human system interface is both a way of giving the orders, but also monitoring the system and stepping in as needed. The final pillar of autonomy is trust, and trust is really fundamental. Without trust, there is no autonomy. Autonomy is granted on the basis of trust, and if we were together, I would have a bunch of jokes about how I used to put my kids in cages when they were little, because I didn't trust them. They had good algorithm, they had good HSI, but I didn't have a real trust in what they could do. So I would put them in, their cribs and limit their autonomy. But without that fundamental pillar, we're not going anywhere. And really, in today's conversation, I think that's going to be a key element of how do you develop that trust? How do you know your system is ready to be let loose and to give it that freedom that it will indeed do your bidding, both implicit and explicit. But the foundation of autonomy is equally important, and that's this open environment. And this really is what's bringing that whole community together is fundamental. And really, we have to create this open environment in which we can work on these algorithms, HSI, and all the trust elements. But you have to develop an open environment around an open architecture. And I think Matt Duquette at least will mention that as one of the key efforts under SkyBoard is how do we bring that architecture that allows us to pull in a whole set of performers, including small businesses, large businesses, the labs, and everybody else. Part of that open environment is also the modeling and simulation tools. It's the test assets, it's the ranges. All of this is what makes autonomy possible and is critical. I'll just quickly touch on a difference between autonomy and artificial intelligence. It's a common question that comes up all the time. And again, autonomy is a C2 construct in which we delegate some authority. Well, you could delegate the authority to whoever you want. It doesn't have to be an intelligent system. We delegate a lot of authority to a mine. The mine can blow off or not. But we don't consider it intelligence. The difference is that the decision-making for a mine to go off or any other thermostat, any other system that is, in quote, fully autonomous, is that it's a very low complexity system. It doesn't have a very complex set of decisions to go through to make that final action. So if we want to go beyond the trivial complexity and still have, grant a lot of autonomy to the system, we have to increase the level of intelligence in that system. And that's intelligence is the ability to reason over a more complex set of inputs and potentialities. So autonomy and intelligence are two orthogonal axes, but you will not achieve a great level of autonomy in a complex environment without adding a lot of intelligence into the system. Finally, I'll touch on the objectives. Why do we do autonomy? And it's mostly to go faster. 20 years ago when I started, a lot of the argument for unmanned was to reduce the manning. And we've realized since then that it was actually disappointing from that perspective. But I think we still need to work very significantly on increasing the speed and the quality of the decision making in combat and also in business operation. And that applies, by the way, to the R&D phase. We also in the R&D phase need to go faster and deploy that autonomy faster. Next slide, please. So how could we do that? And my recommendation is to really look at doing an incremental deployment of the capabilities, very similarly to what the autonomous car industry is doing. You and I cannot go and buy an autonomous car today, but we can buy a car that has a lot of autonomy in it. When they are developing adaptive cruise control and lane keeping and self-parking and all of those features that you can get in your car today, that is working towards an autonomous system in the future. I think the same needs to happen both in Agility Prime and in the Air Force altogether. This allows us to bring value to the airman early. It builds that trust factor that really is fundamental. And it allows us to design better systems because we use them in real life. Many times in the military and in other systems, actually, we are not able to do all the testing that we want, and we have to rely more and more in the modeling and simulation. I apologize for the acronyms here. Modeling and simulation and live virtual constructive are going to be critical factors in the future of autonomous system design and validation. And I continue to urge people to do more of that. Next, please. This I won't cover it in details, but some of the big challenges that I think Agility Prime is really looking at addressing are in the testing, evaluation, verification, and validation, TEV&V for short. And really all the elements of the framework bring a level of challenge, whether it's in the algorithms that we need to have more and more intelligent system, which means more and more complex algorithms, or in the human system interface, where we want to really enable appropriate level of judgment, but also reduce the cognitive burden on the people, in trust factors, from all the way to ethical elements, which I think are critical. And finally, in the open environment, modeling and sim is far from being as capable as we need, and we need to continue to develop new methods. As a last note here, I wanted to, next slide please, I wanted to make sure people are aware that the DoD has a community of interest on autonomy. And in particular, we have a working group on TEV&V, and I encourage everybody to join that community and work. This is across the DoD, all the services and agencies participate, and it's led by a great guy, an Army guy, and I think they can make a difference. So if you can, Frank, you can go to the last slide. And finally, I think another key element, and that is really at the center of the trust question, is the ethics, and I think it's going to become more and more important. As I'm sure all of you are aware, the department has adopted 5 principles to designing ethical systems. And I think it's going to become more and more central to everything we do for both autonomy and AI. And that's it.
All right, JC, I appreciate that. That was a really good oversight. I think that you know, with your experience, it gives us a good introduction to this space. One question I had for you was, so based on your experience and what you've seen happen over time, where do you see autonomy, especially in terms of the urban air mobility mission, where do you see it in 5, 10, 20 years? Oh, there.
So yeah, I guess it's actually a lot easier to develop autonomous system for aerial application than it is on the ground. So I think the chances of us seeing an autonomous taxi, if you will, an autonomous aerial taxi, is in that time frame is much better than a ground taxi. Maybe with one caveat, and I'd love to hear from our attendees, but maybe the caveat would be the level of funding that the ground autonomous systems are getting is astounding. But I think the challenges that we have to solve are actually a lot more doable. Having a third dimension really makes things more doable. So, you know, you're asking me for prediction. I would say there's still, and it will be great to hear what Wes has to say on that from the FAA perspective, because I think there will be quite a few technical hurdles, but also quite a few regulatory hurdles before we get to a fully autonomous system. And what I believe really is important is to go for an incremental approach where we continue to reduce the number of actions required by the pilot, potentially reduce the number of pilots, but really adopt an incremental development approach very similar to what the ground vehicles are doing.
Great. Thanks, JC. I really appreciate that. And that's an interesting answer. I don't know that you'd hear many people in the world of Tesla and Ford say that air taxis are going to get there before they do, but I definitely understand where you're coming from, and that third dimension does add an interesting element. And just to keep us on schedule here, I wish we had more time for more questions, but I want to keep it moving. And JC actually gave me the great introduction, the great segue for Mr. Wes Ryan, who is the FAA lead on unmanned and pilotless aircraft technology. So without any further ado, Wes, I'm going to go ahead and hand it over to you for your inputs.
Okay, great. Yeah, I don't have any slides to share, but I do have some opening remarks I'd like to make. And just first, I'll say thank you for including me in this distinguished panel. Really looking forward to the discussion today and the question and answer. You know, we get lots of questions in the FAA about when things are going to happen, how fast things will happen. All we can say in response to that is we've got a pretty well proven track record and methodologies for bringing new technology to certification and getting those technologies into operational use in a safe manner. Historically, we've brought a lot of new technologies, especially in the general aviation industry over the last 10 to 20 years, that have really greatly revolutionized the way you know, small aircraft are flown. And a lot of times we used to have to wait on technology to trickle down. Now the smaller aircraft industry and maybe this advanced air mobility market will become the test bed for a lot of new exciting technologies to work their way up into other types of aircraft. Our shared challenge, of course, is we have to make sure that we're not only just considering the aircraft technology itself, but how it will be flown in the national airspace system, the training that's required for the people that will operate those aircraft, and a focus on not disrupting our current safe civil operational use of transport aircraft and general aviation. And so our primary focus is on that safety goal, but we also recognize the possibility that technology brings to the table to enhance safety, to increase the utility of aircraft and how they're used to also increase the access to aviation, potentially making aircraft easier to fly, making more people want to become pilots, or for some of the advanced air mobility concepts, taking advantage of automated air taxi in the future. So there's a lot of these future flight concepts that are very exciting for us. We have our Center for Emerging Concepts and Innovation that we have started up to work with industry to get involved very early in the certification process, to try to line up a company's great technology ideas with a feasible model of how that technology could be brought safely into our existing airspace system. And we've had a lot of great success also from past partnerships. So we're very excited about Agility Prime, the NASA National Campaign, and working with industry and academia to bring some of these new ideas to fruition. One of our challenges, of course, is proving the automation is capable for repeatable, reliable, certifiable civil use. And part of that challenge is creating the certification requirements and compliance requirements, to put that process in play, to find clear paths for certification for people to bring new technologies. And so it's key for us to focus on the development of industry standards in partnership with NASA, with industry, with academia, and putting acceptable design and safety standards in place. Proving a technology is capable of being used for civil use is a step beyond just showing that it's ready for a technology demonstration. And so one of our interesting challenges is we've had great technology demonstrators for automation that have been flown in the past, that are showing that automation technology is becoming very, very capable. But also having that technology respond in a real operational environment to contingencies, to weather, to all the things that pilots encounter today. It's a challenge for everyone to look at that list of tasks and safely design systems to take over those tasks. And one of the most exciting things that we're working on in partnership with industry right now is considering some of the new design methodologies for development of complex systems, for software, for automation, runtime assurance, and some of the other really important key development technologies for complex systems, helping the systems be self-aware, or at least self-checking so that they can respond to contingencies and continue to function. Those are all things that are really important for this next step to reach our safety goals along with these future automation goals. And going from a technology being just assistive or assisting the pilot to becoming now responsible for the safety of flight is quite a challenge. And we're really looking forward to discussing that today, and then moving past that discussion into our certification projects with our applicants and with this project as well. I'll close with the idea here that some of those new methodologies are looking at high fidelity simulation, hardware in the loop simulation, new development tools for software, things that maybe in the past have been used on some of these complex technology demonstrators, but are not always the case, being applied to small civil general aviation aircraft, for example, because the cost of those types of development technologies and testing technologies were very expensive. So with the computer age and with all the new sensor technologies and data processing technologies, there's a really exciting, emerging capability to be able to bring some of those new development techniques and new technologies into our system safety and system development and certification processes. And so very much excited to have the conversation today on automation, but also focusing on system architecture and how that plays into the safe implementation of automated systems towards this future of autonomy. So thanks very much for the opportunity to be part of the discussion, and I'll end my opening comments there and ask if there's any questions that anyone would like to ask at this point.
Thanks, Wes. I imagine you get to see some pretty interesting and innovative designs there with everybody coming through the FAA.
Yeah, absolutely.
One of the questions we did get was, can an oversized drone get FAA approval for flying over people in cities? And I'm going to caveat that with, as an airworthiness guy, you know, is it really design and airworthiness standards that are the problem, or is it the maturity of the automation technology that's kind of quote unquote holding up the autonomy certification?
Yeah, that's a great question. And, you know, we kind of get both flavors from, you know, talking to some of the industry. Many of them that are just in early stages of development will say, oh, you know, there's a lack of standards, there's a lack of standardization, there's a lack of, you know, design requirements or airworthiness requirements. And so oftentimes they're waiting. But on the other side of the coin, we've seen great success with companies who are willing to go out and spend some money to build a prototype to begin doing some limited experimental operations. For example, partnerships like Agility Prime will help us move some of those types of demonstrator technologies forward, maybe in a slightly different risk model than what the FAA might currently have. But, you know, to specifically say, you know, whether it's the holdup of cert requirements or the maturity of the technology, it's a parallel path development for both. It's a shared challenge that we have for both. And the prototyping process means, you know, getting a technology out there, testing it, doing more than just a technology demonstration on a subscale prototype, for example, because getting to that end goal of a larger drone or unmanned aircraft flying over a populated area and getting a design certification from the FAA to do that safely, along with the operational approval that is part of that, you have to, you know, show that it can be done safely. And that doesn't mean going and flying 1 million flight hours in some remote area, but it's a review of the design, it's a review of the operational procedures, the training, the characteristics of the aircraft and how it responds to failures, and having confidence, or what we call safety assurance, of a system being ready for that type of operation. So in a nutshell, the answer to that question is yes, there is a process to get there. The type certification process for any civil use aircraft is in place and is ready to be exercised. And we have quite a few companies that are going through it right now with that future intent of flying, you know, in populated areas. One of the big technology challenges that remains is the detect and avoid technology, and to fly in a populated area also means populated airspace or busy airspace. And doing that job and replacing that task of, you know, having the pilot responsible for separation to now putting that technology in place of the pilot and saying the technology is responsible for traffic separation, there's a lot of work to be done there yet. So it's a great question. Looking forward to, you know, trying to get there in the future.
That was a great answer, but the flight test side of my brain got even more excited because all I heard was you got to go flight test if you want to actually get any of these certified.
Yeah.
Well, I appreciate that.
There's a really interesting development loop, as I tried to mention in my opening comments, that, you know, you test a little, you design a little, you know, there's a loop of test and fix and change the design and go back and test some more and fix. And we know that some of our certification processes are not as agile for some of that, you know, iterative loop on a design. And so we're working to try to be more agile in those processes for software and hardware certification, things like that.
That's great. Yeah, and in fact, that gives me another perfect segue into the next speaker as we move on. Thanks, Wes. I really appreciate that, and it's always great to hear the FAA side of this as well, especially on, you know, an Air Force program, but this is really a program for the entire enterprise to look for solutions to get there. But speaking of, you know, iterating on solutions for autonomy, we've got Mr. Matt Duquette, who is the chief engineer for the SkyBoard program, which is one of our, as I mentioned, our vanguard programs in AFRL that is looking specifically at developing some autonomy that is really, and Matt, you can correct me on this, but it's really intended to be almost hardware independent and more portable between different platforms. And he can give you some of the details on that, but I think that kind of speaks directly to what we were talking about in terms of iterating tests so that we can develop certification standards.
Yeah, thanks, Frank. That was a great intro. You're right on with the things that you said, and I think I get a chance to build on some great things that JC and Wes have said about the challenges and the opportunities with autonomy. So the Air Force launched on the SkyBoard program as one of the first 3 Vanguard programs, which means that we go beyond the research and development and focus on how we transform operations through the application of a new technology. And we're really building on a number of years of autonomy research within AFRL and across the DoD and in academia and industry as well. And in a lot of ways, I would say finally pulling the trigger to build an autonomy system. And so what we recognized early on is that designing autonomy for a single platform or a single mission is somewhat of a wasteful venture, because we know that so much of what we need to develop applies to a number of missions, a number of platforms, and designing for flexibility and openness and transferability between various different aircraft is key. And so the SkyBoard program is definitely at to reuse the term, the vanguard of autonomy development in the Air Force to do exactly that. So what we're trying to do is look across the industry, develop a best of breed approach that has those key attributes of openness, of flexibility, while maintaining a high level of security and assurance. And so what we aim to do is build a system where we actually strengthen industry, we strengthen the overall ecosystem by having a framework where folks can bring, for lack of a better term, an app to do an autonomous function. And so as technologies prove themselves out, we can replace certain functionality with new, better, more specific functionality for that application. And then the other thing that SkyBoard is doing with its autonomy system is building in an assurance layer. And JC spoke to trust as one of the key pillars of autonomy. And understanding that whether it's a basic algorithm, something like a Dijkstra search algorithm, from the 1960s, or if it's at the very cutting edge of machine learning, no matter what algorithm we bring into the system, we have to have some kind of safeguard that can fall back to a safe maneuver or something that's highly robust, highly guaranteed. And so we're building that runtime assurance, as we call it, into the system as a watchdog. There's an old aviation term that the 3 things you do when you fly is you aviate, you navigate, and you communicate. And really, from an autonomy perspective, we have to make sure that whatever we develop or whatever we integrate into the system can do all 3 of those things effectively. And if we find that it's starting to operate out of bounds, then we have to call another flight test term, knock it off, where you cut that autonomy out of the loop and you go back to something that's more guaranteed and often a much simpler type of action, until you can return to a state where, again, you trust the autonomy to take over. And so those attributes have really pushed the SkyBoard program to pursue a framework that draws from all of the things that we've been doing, in the DoD and in industry, to enable a number of different autonomous functions to come together into one system. The other point I'd like to make is SkyBoard. If you follow the press, we're generally focused on higher speed, more capable combat UAS that can go do a number of Air Force missions. But I'd like to say that most of the technology that we're pursuing can apply to an orb, can apply to a small UAV, and that's really the idea of the family of systems approach. Whether or not you have a route planner or a mission task allocator, something that executes commander's intent, those kinds of functions can easily apply to a small UAS as much as a heavy, fast-moving, high-altitude, highly capable system. And that's the idea behind the SkyBoard system being so open and relatively generic, is that it can apply across these various different programs and then the Air Force can invest once and reap benefits, over time. The other thing it does is it creates a healthy ecosystem where if folks are looking at an autonomy architecture and helping to improve it, we aren't going off in our separate camps and developing forks or incompatible systems. That we're actually developing things that can interact with each other and fit into a single system.
Thanks, Matt. Yeah, so it sounds to me like what SkyBoard is looking to do is create almost an OS that can support apps from different places to come in and be used in the aircraft or whatever the system is, which I think is, obviously it's a model that's been proven out in other industries as very successful.
Right. Yeah.
So what do you see in terms of challenges with respect to coordinating actions between those apps when you start to get, multiple autonomous functions trying to do different things at the same time and having to coordinate those things and keep everything in line? What kind of challenges do you see with respect to that on SkyBoard?
That's a great question, Frank, because that's a fundamental architectural challenge, I think, with autonomy is how you make that decision. Really, autonomy kind of breaks down in very simple terms into you have a set of requests that come from a commander. Let's say you have a team of UAVs, and that team has to then allocate the tasks among the team members, and then you have to go execute those tasks, and then you have to monitor the execution of that and make corrections. And so that hierarchical approach in the autonomy architecture really calls for a flexible way to insert decision-making algorithms and decision-making modules. Insert your favorite term there to enable that kind of behavior. So that the key point I think is that whatever we develop has to have clearly defined and extensible interfaces between components, and the other thing it has to have is a very clear architecture for how that decision is made. We're moving down that path right now with our contractors and developing a centralized architecture, if you will, for the autonomy system that we can then hang these various modules on.
Sounds great. Exciting stuff. I'm looking forward to seeing some of the stuff come out of SkyBoard and start to see it actually operating in the air and doing some really interesting things. So unfortunately, Matt didn't give me the segue like the other speakers did, so I'll have to give you some of that feedback afterwards. But I want to move on to our next speaker, Dr. Stephen Cook, who, as I mentioned, is the Northrop Grumman Fellow in the Independent Office of Airworthiness there at Northrop Grumman, but more importantly, he's leading some of the certification more the standards development in the AC 377 group there, looking at autonomous design and operations. So I'm going to go ahead and pull Dr. Cook's slides up, and Steve, hand it off to you to start your talk.
Thanks a lot, Frank. I really appreciate you including me on the panel, and really did want to talk about today the importance of consensus standards and how we believe in ASTM and in industry that they can really be helpful in supporting the deployment and safe execution of autonomous functions on aircraft. One of the challenges we have, Frank, if you'll just go to the next slide, is the pace of technology. And the current regulatory environment in the United States really is challenged by the fact that the technology is moving faster and faster than ever before. And what used to be a longer term cycle where we had a chance to get the regulations around the technology now is just moving so fast. If you go to the next slide, the solution to that really is, we believe, is consensus standards. Groups like ASTM, SAE, RTCA, other standards development organizations that fortunately both the FAA with the Part 23 rewrite and the military through Mill Handbook 516 has performance-based, risk-based approaches where they can adopt consensus standards or use consensus standards as a means of compliance to their regulation. So industry standards can move fairly rapidly. We can usually churn out standards in a matter of 6 to 12 months, whereas rulemaking and changes to policy typically take a lot longer than that. So this is really a key. We believe that consensus standards really offers us a way to help regulation keep up with the pace of technology. And next slide, if you just look at where we fit, ASTM in particular has 4 major aircraft standards development organizations: F-37 for light sport aircraft, F-38 for unmanned aircraft systems, F-39 for aircraft systems, things like angle of attack indicators, for instance, and F-44 for general aviation aircraft. And AC-377, which stands for Administrative Committee, 377 for Autonomy Design and Operations in Aviation. We really try to help the standards be transferable between the group. Wes mentioned earlier, detect and avoid. So we could have a detect and avoid standard maybe created out of F-38, but by using common terminology, common requirements framework for certification, looking at essential design pillars, and looking at regulatory barriers in the formation of the standards in F-38, as long as we're using those same types of ideas and principles, this standard could then be adopted potentially for use in general aviation or light sport aircraft, et cetera. So it really promotes this reuse and transferability of standards. And this kind of goes a little bit to what Matt was just talking about, of being able to have more of an open approach towards towards autonomy and systems that are going to enable autonomy. Next slide. So we put our guidance and our recommendations out in the form of technical reports. Our first technical report is out on the street right now. It focused on terminology and a requirements framework. It defines 51 terms related to aviation autonomy. It makes a recommendation that instead of looking at the automotive industry's model for levels of autonomy, that we really look at more of a function by function approach. We break it down, we decompose things into functional decompositions, and then we look at really 3 key sets of questions, next slide, with regard to that. So the first set of questions that we look at are, what is the risk versus the benefit? And one of the things that we've looked at there is the auto ground collision avoidance system on the F-16 and the F-35, and looking at the trade-off between what the technology brings to the table versus the risk of having an incapacitated pilot, and looking at that risk-benefit ratio and saying, if this system is really going to be a save-the-day system, you know, how does that help us tailor the means of compliance to put it on the aircraft in a way that's going to buy its way onto the aircraft and promote safety? We need to understand the role of the automation, kind of going back to what JC was saying. We really want to understand how the human, either the air traffic controller or the pilot or the maintainer, any of the human interface with that autonomy is going to be performed, because that is an essential relationship. And lastly, what's the maturity? What's the complexity of the autonomy? Is it a simple wings leveler autopilot, or is it something a lot more sophisticated that's going to have a lot more true autonomy versus just automation? And so by looking at those 3 sets of questions, which are in our technical report, it helps our standards committees understand what level of rigor needs to be put into the means of compliance for that particular system in that particular role. So that's what we recommend for our standards committees out of the requirements framework. Next slide. The forthcoming, and it should be actually available either this week or next out on the ASTM Compass website, is looking at fundamental development pillars for increased autonomy. And we've looked at 6 things that we feel are really fundamental to implementing autonomy into aircraft systems. One is the development assurance process, looking at not just the standard DO 178 type of approach for software, but also looking at approaches for non-deterministic systems, for systems that really can't be certified using traditional approaches, and what that might look like, what development assurance might look like for those systems. Looking at best uses of modularity and partitioning, looking at the use of runtime assurance. F38's actually produced a standard, F3269, on runtime assurance that's being actively used in the community. And what would be the lessons learned, the ways that we could implement autonomy using a certified runtime assurance safety monitor on top of that autonomy. Looking at best practices for fail functionality and redundancy. Looking at dynamic consistency checking on the sensor inputs, making sure that they make sense, that we don't, for systems that implement things like neural nets, that we're not putting in bad information for that system to use. And then finally, right in the center is that operations in the human role, going back to what JC was talking about, of that human being right in the center of the Venn diagram. So we encourage everyone to check out that report when it's released, either this week or next. Next slide. And the last effort that we've got going on as part of our holistic approach is a regulatory barrier analysis. So we're looking at, we've done a preliminary analysis of 3,171 lines of Part 91 General Operating Rules. And that team in AC377 has looked at categorizing them as large barriers to autonomy, regulations that might need tweaking, regulations that might slow the process, and regulations that are consistent. You can see the initial pass of that result. And their report's going to be coming out later in a few months, but looking at potential ways of writing standards that's going to be consistent with the Part 91 and being able to overcome some of these barriers. Next slide. So in conclusion, you can just go ahead and build this out, Frank. You know, we do think that autonomy has the potential to transform aviation. We're really excited about what Agility Prime is doing here and how they're partnering with some of the leading manufacturers. And we just think that there's tremendous promise here. We think that consensus standards can play a big role in keeping pace with the technology, because it's just accelerating more and more. We think common terminology, being able to understand what we mean when we say automation and autonomy and other key terms, as well as using a harmonized requirements framework, are critical in this standards development. We think that the foundational pillars of autonomy need to be included in all of our standards and need to be considered, and those best practices that have been developed throughout the years, we've got to learn from those. And then as we move into this next era, be able to build on those. And then finally, we're looking at those regulatory barriers and looking at ways to write standards to be consistent or to make recommendations to move those regulations forward. And the bottom line is that our group consists of folks that are in the major industry for AAM, for UAS, traditional manufacturers, regulators, academia, and it's a fantastic team, and they've done tremendous amount of work. And we just think that by bringing the community together and looking at consensus standards, we can move aviation forward into the age of autonomy. And Frank, with that, I'll hand it back to you and take any questions.
So I've got one question to start off, and just wanted to get your thoughts on, it's really kind of the so what, right? So
yeah,
what are your thoughts on why industry consensus standards are important to, you know, the civilian and the military airworthiness processes?
Yeah, that's a good question. So both the updated Part 23 is a performance-based standard. It moves away from prescriptive standards. So it really opens the door for the use of consensus standards to be able to show means of compliance to the regulation. So it gives the regulator something to point to and say, all right, industry has come together with the regulators in the room, with pilots and other key stakeholders in the room, and said, this is what we believe is a good standard for this. And they can take that as at least as a starting point for negotiating that certification basis. The military process is not that different. Mil Handbook 516 has a list of airworthiness criteria, standards, and means of compliance that can all be tailored. And it lists consensus standards that can be used as a part of that tailoring process. So we just think this has a real potential to be able to help get these flying orbs certified, whether it's a military process that you might use, Frank, or a civilian process that the industry might use and be working with Wes on. So that's why we're so excited about it.
I appreciate that. And I asked that question kind of knowing what the answer was, because as an airworthiness guy, and Matt Dilsaver can probably back me up on this too when he gives his introduction here, but anytime that somebody walks in and starts talking about, okay, I want to get my aircraft certified for whatever they want to do from a military perspective with 516C, if you can point to a set of standards, even if they're not necessarily standards prescribed in 516C, but they are industry standards, that's only going to help your case. And like you said, you've got users, you've got maintainers, you've got builders, you've got safety guys, you've got everybody coming together and saying, these are the things that we think are important. And so I think that really does help when it comes to trying to get to certification. So, so Steve gave me a great segue there. So Matt, I'm going to have to come back to you, but moving on to our next speaker here, we've got Dr. Matt Dilsaver, who not only is he right now working on some of the unmanned teaming type things, so definitely looking at some of those trust issues in autonomy, but he was also, prior to that, he was a 516C SME on flight control. So he understands kind of the nuts and bolts and the sausage making of airworthiness from a MIL 516C standpoint. So he's got some really valuable insights into both autonomy and the airworthiness certification side of things. So Matt, when you're ready, I'll go ahead and switch over to your slides so that you can start going here.
Sure. Thanks, Frank. So yeah, I'm going to talk a little bit today, kind of, I guess, building on what a couple other people have talked about, looking at certification, kind of the certification challenges, certification methods for autonomous functions, really though, taking more of a look at the military side of it, as opposed to say what Wes would be doing on the civilian side. So next slide, Frank. So I think one of the major issues with certification, or one of the major things we're looking at, is we want the system to perform as designed. We want the system to do what we expect it to do, I guess. And so this is a very important issue for the Air Force as a whole. So important, in fact, that we just had both myself and JC supported a Air Force Scientific Advisory Board study that's just completing, and this comes directly all the way from the Secretary of the Air Force has to approve this. It was titled Understanding and Avoiding Unintended Behaviors in Autonomous Systems. And so basically what we did, at least for the first couple of months before we got shut down, was we met with academia, industry, and military organizations, first in person and later on more virtually. And so we were charged with doing several things. Looking at past cases of unintended behaviors, both commercial and national defense. So that could be anything from the Boeing 737 MAX, which you could argue was an issue with autonomy, or you could make other arguments as to full system issues, but all the way through, some of the Tesla incidents, to even something like Microsoft Tay AI, if you're familiar with that. Next thing was also, we were looking at current theoretical frameworks to assess software logic errors in high dimensional or near infinite state software systems. So how do we deal with some of these, as we start adding in things like AI or machine learning, and we have really non-deterministic now software systems, what kind of approaches can we look at there for possibly certification. Another big thing is evaluate software architectures. So really I think, a lot of it is really how you architect your system. I've heard runtime assurance talked about a couple times, and I think from a couple other people, and I think it's important that you really architect your system in a way so that you can use the entire architecture to show safety. And then finally, to assess current and foreseeable approaches for detecting, alerting, and avoided unintended behaviors, and also for increasing fault tolerance. So from being on the panel and kind of traveling around and listening to a lot of very smart people talk, the actual panel findings and recommendations haven't been approved yet. So I'll give you my personal, this is Matt Dilsaver's takeaway, not necessarily the views of the US government or the Air Force, but I really think we need a combination of design time and runtime. So it's looking at, using things like formal methods. To maybe certify your runtime techniques. So I think we can all agree that having runtime protection is great. But how can we ensure that the runtime is actually protecting us? And so we might be able to use things like formal methods to show that if certain conditions are met, we can guarantee that certain safety parameters are then followed, essentially. So really, I think it's a full architectural, combination of both design time and runtime. Next slide, please, Frank. So looking at, kind of military certification of autonomy. So we have a working group that we've been working for several years now that Frank's actually leading up, working both AFRL and Air Force Lifecycle Management Center, trying to find an approach for certification of autonomy. And so for those of you who don't know, essentially military airworthiness is guided by Mil Handbook 516C, which contains, hundreds, maybe over 1,000 different airworthiness criteria, everything from structural criteria to your electrical systems to, anything you could think of. And so, I've heard people already mention, some people will say, well, these criteria really aren't set up for autonomous functions. We can't use them. We need new criteria or other things. And I would actually disagree with that. In most cases, the criteria themselves are general enough that they could be applied. So I just threw out a couple of examples here. 6214 says verify each function integrated in or by the vehicle control function, essentially your flight controls, and design is safe. There's nothing in there. If you have an autonomous function in there, you now will have to figure out a way to show compliance with that. Or the next one, verify the effects of loss of function on safety. So you still have to do your functional analysis, to look at how can I show that if I've lost this function, that how does that affect my safety and how can I mitigate that loss? And a good thing about the military process is, and I think it was mentioned earlier, is so these are the criteria, kind of the motherhood is good kind of, very high level things. And then we have, standards and methods of compliance underneath that. But we are allowed to change, to modify, with approval, of course, but we are allowed to change the standards and the methods of compliance. So you could, as Steve mentioned before me, you could pull in something from, say, an ASTM standard and present that to the airworthiness authorities and say, okay, so I need to show whatever, 6224 here, the effect of loss of function on safety. I'm going to do that by applying this industry standard and then showing, and then you have to then tell method of compliance, what artifacts I'm going to use to show that I've complied with that standard and criteria. So I think everything really is there. It just takes, maybe some creativity is the right word. You just have to kind of look at this and show, and be able to come up with a story on how can I show compliance with this. And another good thing, I guess, especially I think for autonomy, is that the military approach is inherently risk-based. So you don't necessarily have to show compliance with every single criteria, But so if you're non-compliant, then we would do a risk assessment. So then you have to show, okay, well, maybe I can't actually meet this criteria, but I have done some things to mitigate that so that you can show then that you've lowered it to an acceptable level of risk and still get that signed off. And there's many sections in there that require examination, from things like flight controls, diagnostic systems. Section 10 has a bunch of things. So, how can I show that my functions are working or are not working? How do I know? Another big one is Section 15, which is software systems. How do I, algorithms are one thing, showing that I have good algorithms, but then you also have to show that when I take those algorithms and I turn those into code, that I've done that in a sound process, essentially. And I'll give a quick look here. I wrote this paper a couple of years ago. It's not a great paper. I'll be the first to admit we wrote it in like a week to meet the deadline, but I think there is some decent things in there, and it gives a little bit more of a discussion. And if you're interested, you can probably get something useful out of it. It was written for adaptive controllers, but I think it can generalize to more autonomous functions. So next slide, Frank. So real quickly then, I've heard a couple other people mention it, but I think a key point here is we can't forget about the humans. A lot of people think autonomous, automation, autonomy, hey, it's software, it's unmanned, there's nobody in the loop, and that's just not true, right? When you start looking at accidents and incidents, one major cause is still the humans. It's overtrust, it's undertrust, it's misunderstanding, it's not actually fully understanding what this autopilot mode is actually controlling and what the pilot is supposed to be controlling. And so, there's still, until we get to, using the car, level 5 true autonomy with absolutely, the airplane, everybody steps in and takes a nap and you wake up somewhere else. There's still humans, and I don't like getting into these arguments, just like I don't really like getting into an argument on what does autonomy really mean. But there's humans in the loop, on the loop, around the loop, supervising the loop, whatever. There's still, even if it's just translating human intent into your system, there's still some sort of human doing something in your system. And so I think it's very important, that you present the humans with the information needed on the system states as well as system health in an understandable way, so that the human, especially if they're kind of monitoring multiple systems, they need to quickly be able to look and see what's happening, why it's happening, and that things are happening, kind of in a predictable manner. And I think that's all I've got, Frank.
That was great, Matt. I appreciate that. And I really do think that the human part of it that you mentioned is really important. That's something that I think is sometimes maybe overlooked, probably not intentionally, but the focus tends to be on the autonomy itself, right? And not necessarily about who's having to interface with that autonomy. I always like to say that people use an autonomous system on a regular basis without even really thinking about it, because the interface is so good, and maybe not so much now that COVID's happened, but when you get into an elevator, you're getting into an autonomous system, you're putting your life in its hands, your controls are very simplified, your feedback is very simplified as well, but everybody's very comfortable with that because the trust has been established and that interface is good. Have you seen, or do you expect to see maybe new standards or new methods of compliance needed on this unmanned human machine interface side of things that maybe need to be developed?
I think it's honestly a case, and I'm not an HMI expert, but I think, especially looking at things like, when you start looking at 516, the pilot displays, I think once again, from the top level, the criteria are all there, most likely on presenting safety critical information to the pilot. So I think maybe we would just need to look at how we modify those, how we adapt those for more of an autonomous, more of a supervisory role for a human.
Yep, that makes sense. All right, I appreciate everyone for your time. participating today. Now I'm gonna go to the question bank here, and we're gonna start throwing some more questions out there. I'll try and send them to people specifically, but please feel free to chime in if you've got something to add. We've got some really good questions that were out there. So let me run to the first one here. This is kind of a longer question, but by focusing so strongly on autonomy for unmanned aerial systems, are you making a bigger hurdle to getting unmanned in the air versus a new manned concept? Autonomy is not unique to unmanned, and the UAM Agility Prime gets into that mix of unmanned, but really manned, and having pilot or ops manager at the ground segment ops center versus on the aircraft. So that's really kind of speaking to the progression of starting off with manned, going to some kind of maybe off-board, but still manned in the loop kind of solution, to then maybe manned on the loop, more of a monitoring kind of approach. Maybe JC, do you have some thoughts on that?
No, that's exactly right. That's the point I was trying to make earlier, is that although the objective might be to have an unmanned system eventually that functions at a very high level of autonomy, we shouldn't wait until we have all of that figured out to start deploying autonomy in the real world, where one, we can improve the life and safety of the pilot and the passengers. But also, learn how it actually works. Because, I mean, a lot of the test environments are relatively sterile. And that's why, at the end of the day, the Waymo and Uber and all of the other autonomous car makers, they built a fleet of vehicles to put on the road. So how do we get there? In my view, is by implementing more and more autonomy in an agile manner, as Wes was mentioning, and really ramp up that level of autonomy. Eventually, we get to the point where the interfaces are so simple, the level of safety is so high that we are okay with without having constant monitoring and a highly trained operator.
Thanks for that. Yeah, so I've got another one here, and Wes, I'm gonna tee this one up to you, because you may have seen some of this already on the FAA side. But how do we handle accountability and liability when it comes to these autonomous systems? Have you heard anything about that?
Yeah, it's a really interesting discussion, the ethics of automation and who's responsible, because it's not just an ethics conversation, but also a legal conversation. We have currently Part 91 and other operating requirements in place that basically say a human has to be in charge of safe operation of the aircraft. So from a legal standpoint, our current regulations rely on human interaction with the system to have safe outcomes. That's not to say that we won't allow, an increasing level of automation to achieve a goal, a task, a mission element, whatever it might be. But ultimately, I agree with some of the other commenters on the panel that it's probably a very long way for us to get to what would be truly called autonomy, and not even sure that could ever truly exist, because really, if you pre-program something, it's still not completely autonomous. There was somebody programming the system to do a certain thing with a timeline or a temporal shift in time between programming and execution. But the FAA is looking at that ethical question, at that legal question, also societal acceptance for having automation in charge of an aircraft versus a human pilot. All of those play into the difficulty of not just the technical challenge of moving towards future higher levels of automation and autonomy, but also making sure that society will accept such a thing from a safety standpoint.
Yeah, all important parts of that. I think that's a stickier question, and thanks for filling that, because that's not an easy question to field. But there's a lot that goes into that, and anytime the lawyers get involved, then you know it's going to be complicated. So thanks for that. I had, so let's see, for Steve, this one's for you. They asked, how does simplified vehicle operations relate to functional approach to automation integration in relation to the SAE levels of automation? So I guess really the question I have is why did your team decide to go with the functional approach rather than just adopting the automotive levels of autonomy that we're somewhat familiar with?
Yeah, that's a great question. Ultimately, what we felt like we have in aviation is that extra dimension of communicating. We talked about aviate, navigate, communicate, and that communicating with air traffic, asking for clearances. And so, I mean, if you look at aircraft today, there's already like a FADEC on an engine already does a whole lot of automation on that engine. And so when we talk about the human interaction with the system, it becomes very difficult to just give it a number or to give it a level, because there's all kinds of things on an aircraft that are going on at a variety of, quote, levels of automation or levels of autonomy. So what we decided to look at instead was this framework where we, instead of looking at sort of this whole combination of functions in terms of a experience. I think JC even mentioned earlier, like if you just try and get your arms around what's an autonomous vehicle, it's pretty hard. But if you look at a specific function and you say, what is the function intended, and what am I delegating to the system versus what am I doing what's the human role in that system? It becomes a lot easier in terms of requirements. Instead of saying, well, if you're level 3, these are your requirements, it becomes a lot easier to look at in that particular context of performing that function. What does the level of rigor need to be for the standards that are going to support that function? And so what we believe is by following that framework, it actually promotes more interoperability. So let me give you a quick example. Wes mentioned detect and avoid. So you may have a situation where you want to do automatic or autonomous detect and avoid on a fleet of UAS, but you may want to take that exact same technology and put it on general aviation and just make it an alert to the pilot, so the pilot has increased situation awareness, so then they can make a decision on what path to do to do the collision avoidance or the conflict avoidance. So there's ultimately, we just said, from a standards point of view, what works better for us is looking at a specific function in its specific use in a specific environment, and then writing and tailoring those means of compliance to support this function. That's why we went with a framework instead of the levels of autonomy.
Yeah, that makes a lot of sense. Like you said, you wouldn't think just adding the third dimension adds such a layer of complexity, but when you get into all the things that an aircraft needs to do to fly safely, it's more than just saying, okay, my hands are on the wheel or they're not on the wheel, kind of thing.
Right.
I think, let's see, I've got another one here. Either Matt can chime in on this one. So how do you see the certification process changing for a system that learns or changes over time, sometimes within the time frame of the flight itself?
Yeah, I'll go ahead, Matt.
Okay, so I mean, I think, from a top level, I would say that it doesn't change, right? The certification process is still the same. You still have to somehow show the correct level of rigor and I would say that, online learning, things that are, essentially software that's different when I land than when I take off is going to be very difficult as of right now. You can do things if you have what I would consider offline learning, a system that learns, however, is then locked down, then you can then go with some level of V&V to show some level of compliance with standards. Or depending on what that that system is doing, you have, once again, you have your formally verified runtime assurance that shows that no matter what this function does that's learning online, I can still guarantee safety.
You're on mute, Frank. What was that question?
Sorry, Matthew Cat, did you have anything to add to that besides telling
Actually,
me I'm on mute?
I think Matt Gilsaver hit what my key point was going to be. Our philosophy is that you certify the runtime assurance, and the runtime assurance is really what you know, that's the boundary of the airworthiness. Anything on the other side of that would not necessarily affect your airworthiness. But I would like to say also that I'm somewhat skeptical of online learning for the purpose of actually controlling the airplane and doing aviation navigation types of functions. Where I think the online learning applies the best is in sensor function and understanding mission context. I think there's definitely room for it there. But you know, as far as controlling an aircraft and even handling complex situations, I don't think online learning is required at this point.
That's an interesting point. It's a good distinction to make, because obviously where you stick the autonomy into the system, at least for military certification, makes a difference, right? So if it's a safety critical or flight critical process, that's going to be completely different than just something that's maybe mission critical or even a lower level than that in terms of what you have to prove out in order to integrate that into it.
Yeah, that's
JC,
right.
I've got one. Oh, sorry.
No.
JC, I've got one for you. How do you see some of the unmanned ground vehicle automation, some of those challenges translating, or successes really for that matter, translating into unmanned aerial mobility automation?
So I think there's a lot of great lessons that we can learn from our colleagues working on ground vehicles. A lot of the challenges they have, honestly, is situational understanding, right? Especially in the military context, when we do a lot of roading, you know, is this, you know, a clump of pixels in front of me, a bush that I can drive over, or is it a hard rock that I need to go around? So that level of complexity is something we probably don't have to deal with. And that's why I'm making the claim that AR autonomy is easier than ground autonomy. But I think in general, the approach that they've adopted in the autonomous car industry is really interesting, with shadow mode, where they are deploying new autonomous modes behind the scene and evaluate them continuously. Data collection approaches in which they identify cases where the autonomous system did not behave the way that they thought it should, and collect all the data so that they can go post-mortem or, you know, post-event analyze what happened. A great use of modeling and simulation, both in a traditional manner, but also in kind of taking these rare events and fuzzing them into thousands of new cases, really looking at it. Another approach that I think is useful to emulate is not looking just at accident of autonomous vehicles or cars that were under autonomous control, but looking at all the accidents and really analyzing how would the autonomy behave or would have behaved in this case, and building from those cases. So I think there's really a lot of great lessons to be learned from the autonomous car industry and the ground vehicles in general.
So I'm hearing that robust modeling and simulation is probably key to getting some of these things done, so you can transfer between those scenarios, right?
Yeah, no, I really believe so, especially in the military context, where for various reasons, you know, we don't have the ability to test in the real world. Thankfully, we're not at war. So we don't have a place to go test the real thing anyway. For security reasons, we don't want to do open air testing sometimes. So modeling in sim is critical, but it's also because of all the interactions, right? You're looking at a system of systems where you have a very large number of systems, and bringing that kind of numbers in a real life world, in a real life test, is just not going to happen. We don't have our most complex exercises, I would say, are red flag exercises, and even that is a few dozen airplanes. It is not the complexity of the system the advanced air mobility solutions are going to see. So how do you really correlate that into a complex world? It's going to have to be through modeling in sim.
Great, thanks. Well, thanks to everyone, to the whole panel for participating in this. As you can see, the fact that I still have a load of questions that we didn't get to just shows that we really just scratched the surface here on autonomy, but I still think it was a great discussion. I hope the audience learned a lot from that and maybe queued up some more discussions for the future. So Nate, I'm going to go ahead and hand it back to you for the closeout. I know I'm a minute and a half behind. I apologize for that, but
sure, thanks
for the
fantastic work, Frank, putting this together. Thanks to all the panelists. Please join us next week. We'll have Dr. Roper here, and please don't forget to start looking at those opportunities for collaboration between universities and small business. Looking forward to getting some of those research and development funding opportunities out there. Fantastic discussion today. Thank you all, and talk to you next week. Take care. Goodbye.